Hey there. So last time we took a look at how the character, integer, and the floating point data types are in the C language. What we'll do this time is kind of pick up on other keywords using those three keywords and kind of try and head towards nailing the 32 keywords that the C language provides us. And remember, our intention is that we want to learn the C language by being able to make sense of the assembly that it generates. That's one. And the second is we want to master the 32 keywords and then understand how to use them together. So every program would make sense. At least how it's written, you'll be able to make sense out of it. And that's our intention. So now with that, we can again go back and start our song and dance, which is head to this URL here, which is github.com/in-pyjama/c-ninja-listings. Once that happens, you will land on this repository. Then we want to focus on this button here, the code button. And once you click on this button, there should be like a code space already if you have been following rest of the videos in this series. uh, if this does not exist, then you would need to click on this plus icon here so that you can create a code space, so you have like a working environment. Now that said, I already have this, so we'll then need to go to this triple dots and then okay, we'll need to go to the triple dots and then click on open in browser. Once we do that, it will show up a screen like this, and it will open up the workspace. And I already had one workspace open, so I closed that. The tab that I closed here was that. All right, so let me just full screen it. We don't need any of this, so let's just uh, close all of those. And what I want to do is, so if you create this for the first time, you'll most likely be in the workspaces directory. And then within that, go to C Ninja listings. And then within that, go in the keywords directory. Now, I had some, residual work from the last time. So I'll just do make clean here so that everything is wiped out. There's a lot of files. If you notice, a lot of files here were deleted. The other thing which I did was, I made some changes to the file just before recording this video. So I want to get rid of those. So that's out of the way. This file is now clean. Very nice. Okay, so back to this file here, which is the keywords file. So in the previous video, we kind of reiterated that we have already taken a look at void and return as keywords. Return is used in case of functions. Void we mentioned, we haven't seen like all the possible usage of it. So we put a star there. Then we focused our discussion on understanding in the previous video, that is the character or char, char, float, and the int data type. As a summary of that, what you're supposed to remember for this video is that a char or char is 1 byte long. So total 2 to the power 8 possible bit combinations, right? And different bit combinations represent different things. And we mentioned that you can represent a number from 2 to the power minus 2 to the power 7 to 2 to the power 7 minus 1, right? And this has to do with how the bits are stored. The encoding is in a certain way. Then the integer we mentioned, based on what machine you're compiling your code for, the integer would be at least 2 bytes, right? And usually, typically, it is 4 bytes, right? So let me just make this as 4 bytes. And then we mentioned you can store like 2 to the power minus 2 to the power 31 through 2 to the power 31 minus 1 range of values. And then the last one in our list was float, which again, somehow represented a number with a decimal point, something like 1.0, 2.258. Those numbers are represented using floating point representation. And then we mentioned that the encoding scheme followed is IEEE 754, if I'm not wrong. And then in that, like okay, I should mention before all of that, this was 4 bytes long. right? So 1 bit was the sign bit, then there were, I suppose, 8 bits that were uh, allocated for the exponent, and then there was like 23 bits, um, 23 bits for the Mantissa, right? And the formula was -1 to the power of sign bit into, I suppose, 1 point, Mantissa into, well, 2 to the power uh, exponent minus the base, and the base was 127. I might have gotten this wrong, but if I have, then just take a look at IEEE 754 representation of float, right? And this explanation will pop out. Well, that was like a quick summary of what we did the last time and what you should remember for this time. Now, let me just go ahead and quickly tackle one more kind of, a sibling to the float. So here, remember that, because of this E here, this 8 bits here, our representation is limited, right? And then the other thing is that we only have 23 bits to kind of represent the negative power of 2. What I mean by that is the first bit here would be 2 to the power minus 1. The second would be 2 to the power minus 2, so on and so forth. We come down to 2 to the power minus 23. But that's like the limit on the range. So the double here, this one right here. So if we were to say a variable is double, right? So if we were to say float b equals 1.0, for example, we know that b is 4 bytes, right? And represented, the 1.0 is encoded in this format somehow. Somehow meaning there is some magic that happens such that it's represented in this format. We will take up examples of this format in the later videos to understand how different numbers are actually represented as bits in the memory. But for now, know that this will be represented in 4 bytes using this encoding format for the floating point numbers, which is something like this. So what is double? A double is essentially formally called double precision, right? So instead of storing 4 bytes, the double stores the decimal number uh, in 8 bytes, right? And then much like this, the encoding scheme is that there is one bit for the signed or whether it's a positive number or negative number, 1 bit represents that. Then there are about 11 bits that represent the exponent, and then there are 53 bits that represent the mantissa, right? Again, we'll see the example of this in later videos, but know that because of these 53 bits here, you can go from 2 to the power minus 1 down to 2 to the power minus 53. And again, don't be super critical on me about this. The idea is that you get to represent a lot more finer, what do you say, a lot more, you get to represent the number after the decimal point with a lot more granularity than you would get to do here. Like about 30 bits are extra here, right? And similarly, your exponent, now you can represent like you get 3 more bits to represent the exponent, right? And the bias in this case, so the bias, for example, in float was 127. The bias in this case is 1023, if I am recalling this correctly. And again, please do cross-check this format, the IEEE 754 for float and double precision numbers, and you will get the exact encoding scheme. Okay, so what is the takeaway here? A double precision, a double data type is used to save decimal point numbers with higher precision that the float cannot accommodate, and then it saves the number using 8 bytes, so total 64 bits. All right, so if this much made sense so far, let me just cross out keywords that we have kind of understood so far or taken a look at. Char or char, we have taken a look at that. Double, float, int return void kind of. So we are pretty much done with I don't know, 5 keywords now. 1, 2, 3, 4, 5, 6 keywords down, and we are left with about 26-ish, right? And for rest of the video, let me um, kind of introduce you to siblings of int, right? So in the last one, again, we looked at char, we looked at int, we looked at float, uh, and then from float we also introduced double, and now let's go down and focus on int. So the relevant keywords that are related to int are short and long, right? And then there is some relation to enum, which we'll come to later. Okay, so what is a short and what is a long? So short and long are essentially giving us the width of an integer. Short as a keyword can be used alone. So for example, short a and short int a are same thing. Much like that, long b and long int b are same thing, right? And you can experiment with, can these two keywords be exchanged? Can it be int long? Can it be short int, or sorry, int short? You can experiment with that, right? These are also called okay, never mind, let's not go there. I need to confirm that first. So I'll talk about what I was going to give as an alternate reference to these in the next video. But yeah, so these two are same and these two are same, but then what is short and what is long? So remember, the int could be 2 bytes or 4 bytes depending on which machine we are compiling it for. So a short is 2 bytes and a long is 4 bytes at least, right? So if I were to say short a equals to, let's say, 10, then the compiler ensures that it uses 2 bytes to save the number 10 in the integer format, right? So 16 bits used to save the number 10. Much like that, if I say long b equals to 20, then at least 4 bytes will be used. At least 4 bytes to save the number 20. Now, when I mention long int and short int, it's just that we are specifying to the compiler, hey, whatever your default integer size is, only give me 2 bytes or only give me 4 bytes at least, right? Now, depending on whether our machine is 32 bits or 64 bits, and when we say our machine is 32 bits or 64 bits, we mean that the CPU and the register within it is the register capable of holding 64 bits or 32 bits. Right? We are talking about that. Like what can the CPU, like what width of data can the CPU process? That is what we are focusing on. So depending on 32-bit or 64-bit, a long would be either 32 bits or 64 bits. Right? So remember this. Now there is another type, not type per se, but the usage is long. So if we say long c or long int c equals to, let's say, 100, then what this will do is this will give us 8 bytes. Right? 8 bytes to save the number 100 as an integer. So that's the idea. And this will, like, for sure give us 8 bytes, right? Irrespective of which machine you are on, 32 or 64. So take your time to digest this, experiment around with this. We'll also kind of, experiment locally here to prove some point. But then with this, char or char is out, double is out, float, int, short, long, what else? Volatile, kind of, return. So 1, 2, 3, 4, 5, 6, 7, 8. 8 keywords are out of the 32. We're left with, I don't know, how many? 26. Wait, that was the initial count. We are left with 24. 24 keywords. Now, okay, one other thing to mention is there is a relation between all of the data types, and let me just again redraw it for revision. So we had the C language data types, right? And then the three we looked at was char, int, float, and then within float we said we looked at double, then there was, short, long, and well, long. And then now we are saying that, there are these two keywords, unsigned and signed, right? So there is unsigned and signed as two keywords. And then somewhere I also hinted that enum is also something that is related to int, short. Sorry about the background noise. All right, so we were talking about the C data types, and these are the data types that we have seen so far or discussed about. And I'm again, just showing here what are the keywords that we kind of touched upon so far, right? And then just recently I hinted that unsigned and signed are also related to specifically, these data types here. Like a character can be signed or unsigned, like the 8 bits can be treated as a signed number or an unsigned number. Int can be represented as signed, unsigned, same for short and long. And well, here we also mentioned that there was long, right? All right, so now what I want to do is get on to experimenting with these and demonstrate the amount of space that each one of them would take. And to do so, then let me first, get rid of this. And if you want to try with me, in the last video, we were working with this directory here, the keywords directory, and the foo file, and we'll continue to work with that. So okay, let me just go ahead and open the foo.c. We have our bar function here that we were playing around with in the last video. So let me get rid of all of this, and what we'll do is let's have char a equals to 10. Then let's have int b equals to 20. Then let me have short c equals to 30. Short int d equals to 31. Okay, because I'm running out of numbers, or I'm not able to, um, my brain's not working at this point creatively enough to pick better numbers. Okay, so we then have long de, okay, equals to 32. Then long int f equals to 33. Then long g equals to, well, I don't know, 34. And long int h equals to 35. And then let's take float I equals to 36.37, and double j equals to 38.39, right? So we have these many variables with us from a down to j, and let's quickly take a look at what these are and maybe some predictions about them. So char or char we know is 1 byte. So 10 should be stored in 1 byte, right? And then int in our case happens to be 4 bytes. It's generally 4 bytes. It's just that you should be aware that it need not be 4 byte. Depending on the machine and the compiler, it can be 2 bytes, right? So 20 in our case will be saved in 4 bytes, and we'll confirm all of this. Um, C is 2 bytes because short, and a short int also means that it will be stored in 2 bytes, right? Then a long I mentioned was at least 4 bytes, right? So this is 4 bytes at least. On our machine, it happens to be 4 bytes, 32 bits. So then we have long int, which is same. So these two are same and these two are same in terms of definition, right? In terms of uh, the the size that needs to be allocated, set aside for the variable. So this would be 4 bytes as well. Long and long int are same thing in terms of the amount of space that needs to be set aside. So both of these will occupy 8 bytes, right? And then float we mentioned was IEEE 754 format and 4 bytes long. And double we mentioned was IEEE 754 bytes, 754 format, and uses 8 bytes, right? So, and what I'm going to demonstrate only deals with the size. We'll look at the encoding of these and how to represent decimal point numbers in a dedicated video. Similarly, signed and unsigned video, keywords, we'll take a look at that in the next video, right? All right. So in terms of definition, the keyword should be here. The variable name should be on the right. There should be a space in between. There should be a space in between, different keywords used in C. Long int is not same as long space int, right? We talked about semicolon being the delimiter, separating like the statement in C language. We have also taken a look at what the braces represent, what return represents, all of this in the previous video. Okay, with all of this then let's go ahead and run some commands. So let me get rid of this. I'll press the control and tilde. Okay, just a moment. Yeah, I'll press the control and tilde to get the terminal, and in terminal make sure that you're within this directory here, the keywords directory, this right here and this right here. Okay, if you are there, then simply hit make clean to wipe everything out, any residual files, and then hit make all. Now when I do this, please keep your eyes in this region here. Something interesting will happen. So when I do make all right, some compilation went through. And if you notice, obviously, there are few more files here. This is the one of interest to us. So let me then go ahead and open that file up. Let me close this. This we do not need. This is our bar function. Okay, this is our bar function right here. And then, the assembly or the disassembly, the formal name for this is disassembly. So there is C code and disassembly mixed. We see assembly and C code mixed. And what we are essentially now trying to do is use these numbers here to find out which assembly code might mean what C syntax, right? Okay, so let's go then. Uh, so we had the char or char a equals to 10. So we have 10 being loaded into A5. And from previous video, note that, we talked about the presence of a stack somewhere that S0 register was pointing to. Then the compiler adds some offset, in this case, -17. Well, and, the in our case, let's assume that the memory addresses are increasing in this direction. So from here, you go down in negative direction, 17, and the value of A5 will be stored here, which happens to be 10, right? So this variable A then is at this memory location on the stack, right? And where the variables get stored on the stack, somewhere else, all of that also will cover in the future videos. But for now, understand that variables within a function, this is a very crude way of saying it, variables within a function typically go on the stack. And typical is a very important keyword. Again, why I'm saying typically and when all they can go in different locations, we'll cover them later. A separate dedicated video would be required for that. Okay, so 10 goes here. Then interestingly, B is an int. Int would mean 4 bytes in our case. So 20. So notice that 20 is loaded into A5 and then 20 is transferred to, from S0 at an offset of 24, 20 is saved here. Another interesting thing to look at is the instructions being chosen here, right? So an SB would mean store byte. An SW would mean store word, and a word is nothing but 4 bytes, right? Okay, then we had short C. So again, A5 is the internal register of the CPU on a RISC-V machine. That's what the playlist is dedicated to. So A5, the instruction li is load immediate. So A5 gets the value of 30 here, and then A5 is pushed onto the offset 26, negative 26. This is interesting because 26 is 2 bytes away from 24. And that should kind of also reinforce that this was, we don't know well the size of this, so leave that out. But this was 2 bytes, right? So 30 is stored here. Again, if you notice from 17, 24 is like a huge jump. So why, take that? So what the compiler did was it took it said, okay, on 17th I've stored something. Then 18th, 19th, 20, 21 is where I could have stored an int 4 bytes. But what I'm going to do is to make it easy for me to fetch an integer, which is 4 bytes, let the address be 4 byte aligned. 24, for example, is 4 byte aligned. So what it has then done is skipped these 3 bytes just for efficiency's sake, and then decided to store the integer on 21st, 22nd, 23rd, and 24th byte. And if you see the storage of a short, it's using a 2 byte aligned address. 26 is 2 byte aligned, and 25th and 26th byte is where C will be stored, right? And this is that interesting part that you can take a C code, convert it into assembly, and then start to reason about how things are stored, what the code will do, and so on and so forth. This is also another way of, reinforcing your learnings about the C language, and that's why I like this. All right, so if we see D here, which was a short int, and I mentioned that these two are same. So here you see sh, here also you see sh, by the way, and sh means store half word. A word is 34 bytes, a half word is 2 bytes. And then if you see minus 28 is 2 bytes away. There's a difference of 2 bytes. So then you have 31, which is D stored right here on the 28th offset, right? So this is becoming interesting now. Let me again go and draw like our stack, and then we talked about things until here. So let me quickly scroll up. Let's talk about E. E we mentioned is a long, and F is a long int. Both are same. A long, our case was 4 bytes at least, so 4 bytes. So store word, 32, 4 byte aligned, 36 also 4 byte aligned, from 30, 32, 36 is 4 bytes away, right? So it kind of reinforces that this is 4 bytes. Then if you see long and long int h, both of them are same. Here's the interesting bit. On a 32-bit RISC-V machine, which is what we are using for this playlist, the working registers or the general purpose registers are 4 bytes long, right? The register A0, A1, A4, A5, blah, blah, blah. All of those are 4 bytes long. And a long, we argued, will use 64 bits or 8 bytes. So then the question is, how are we going to save a number that is 64 bits? So the interesting bit is that the compiler has used two registers to save the 60. So let's say this was 64 bits. So the lower 32 bits are saved here in A4. The upper 32 bits are saved in A5, which happen to be 0 in this case. And then it has generated two store word instructions. A word is 32 bits, so 4 bytes worth of storage here, 4 bytes worth of storage here. So it is essentially saving the number between, okay, 52nd, okay, 52nd, 51st, 50th, and 49th. So it's storing here, and it's storing 56th, 55th, 54th, and 53rd. So from 49 to 56, 8 bytes, the number 35 will be saved. And where is it being saved? Obviously on the stack. Somewhere here, there are 8 bytes that are dedicated to the variable h. Right? And this becomes more interesting, right? And if you see here, same story, right? Same story. And if you notice, then this address here, well, at least these two addresses here or offsets here are 4 byte aligned. And together they become like 8 byte aligned if that entire 64 bits is what we are considering. Okay, so then long and long int are same things. Long g, long int g, both same things. All right, now let's come to the float. So float, we mentioned, is using 4 bytes. So forget this line here. We'll discuss about this once we are exploring the encoding formats for both float and double. Here, if you see, there is a store word on what? So store word on the stack, 4 bytes worth of storage. Same thing here. So double we mentioned is 8 bytes worth of storage. So again, two registers being used here, A4 and A5. And there are two store instructions, right? And again, all of this is going on the stack, right? And S0 is the register that is pointing to the stack, and then all computations are at an offset, or all storage is at an offset from the stack pointer, right? And well, this is pretty much, an exit out of the function, and ret is result of the return keyword, which we discussed in the previous video. So that's that. Okay, hopefully this convinces you of the space, the storage space taken by different data type and different ways of defining data types to get different storage. This becomes super useful later on when we are writing like practical C code or practical embedded related C code. You will notice that the data types and the keywords around that are very frequently used, and one should be very thorough with what they mean. And that was the intention of, making a super long video on explaining all of these. In the next video, let's take a look at what unsigned assigned and enum mean, and then we can slowly start to explore what const means, what volatile means, and so on and so forth. And feel free to absolutely play around with the keywords here, change them around, see what happens. You should get a lot of errors or warnings and learn from those errors and warnings. With that, hopefully you had fun as much as I did making this video, and I will see you in the next one. Bye-bye.